Look up on a clear day, and you will see a bright sphere of light keeping our world warm. To us, it feels like a calm, permanent fixture in the sky. But that familiar disk is a cosmic illusion created by fast distance. At roughly 1.4 million kilometers in diameter, this star is a physical behemoth. If you were to hollow it out, you could pour 1,300,000 Earths inside. The Sun holds 99.86% of all mass in our local neighborhood. Every planet combined makes up a tiny fraction of a single percent. This immense structure began 4.6 billion years ago as nothing but a quiet, freezing expanse of hydrogen and helium gas suspended in the vacuum of space. Astronomers believe the explosive death of a nearby massive star sent a shock wave rippling through this cloud. This sudden wave compressed the gas, causing gravity to take over. The densest central region collapsed inward, spinning faster and faster, until it formed a glowing, churning protostar. To understand how this collapsing cloud ignited into the engine that tethers our planets together, we have to travel 700,000 kilometers beneath its blinding surface. Welcome to the core. Down here, the conditions are apocalyptic. The pressure is 265 billion times greater than the Earth's atmosphere, and the temperature sets at a blistering 15 million degrees Celsius. Yet 15 million degrees is actually too cold for hydrogen protons to easily fuse. According to classical physics, positive charges mean they should forcefully repel each other, the Coulomb barrier. But through quantum tunneling, protons occasionally bypass this barrier, teleporting through the resistance to merge together. Because of this tunneling, the core is a relentless engine. Every single second, it smashes roughly 600 million tons of hydrogen into 596 million tons of helium. The missing 4 million tons of mass don't simply vanish. Following Albert Einstein's equation, E equals mc squared, it is converted entirely into radiatum energy every single second. Escaping the core is a brutal process. In the surrounding radiative zone, solar material is so dense that a newly forged photon cannot travel straight. It constantly collides with particles, bouncing along a jagged path known as the random walk. Because of this dense cosmic pinball machine, it can take a single photon of light up to 170,000 years just to traverse this layer. The sunlight warming your skin today was forged during the era of early human ancestors. Eventually, the energy reaches the convective zone. Here, the temperature drops to a relatively cool 2 million degrees, and radiation gives way to boiling plasma. Massive, turbulent columns of hot gas rise, release their heat, and sink back down in a violent churning cycle. This turning is complicated by the way the sun moves. Because it is plasma and not solid rock, it experiences differential rotation. The equator spins in 25 Earth days, while the poles drag behind, ticking 35. As the equator races ahead, the magnetic field lines are stretched, dragged, and twisted into high-tension knots beneath the surface. This photograph shows what happens when those magnetic bands become too twisted. They breach the visible surface, the photosphere, and act like a dam, choking off fresh boiling heat. These blocked regions cool down and appear as pitch-black patches we call sunspots. These spots are highly unstable. When the tangled magnetic field lines finally snap and reconnect, they release their pent-up tension in a cataclysmic explosion. We call this a solar flare. Often, these flares are paired with a coronal mass ejection, where billions of tons of electrified plasma are violently hurled out into space. If that material strikes the Earth, our planetary magnetic field deflects the storm toward the poles, creating the brilliant light shows known as auroras. Surrounding the 5,500-degree visible surface is a ghostly atmosphere called the corona. Visible only during a total eclipse, it holds a lingering astrophysical mystery. The corona surges to temperatures of 1 to 3 million degrees, far hotter than the surface it surrounds. The sun maintains this violent, ongoing equilibrium, a roaring dynamo masked by the calm appearance of a steady circle in our sky. But the physical mechanics of the sun are only part of its story. If you travel billions of kilometers past the planets, you encounter the Oort cloud, a colossal spherical shell of icy debris marking the absolute limit of the sun's gravitational grip. Out here, you can see our true location. We sit in the Orion arm of the Milky Way galaxy, hurtling through interstellar space at roughly 828,000 kilometers per hour. The solar system sails through the galaxy pitched sideways, its planetary disk at a 60-degree angle. Completing its orbit, the Sun drifts through the local bubble, bobbing up and down the galactic disk like a horse on a cosmic carousel. The Sun travels as a solitary vessel, leading a quiet voyage through the vast, dark ocean of the Milky Way. Like all stars, it has a finite lifespan. Roughly 5 billion years from now, the core will finally exhaust its hydrogen fuel, and gravity will begin to crush the dying star inward. As the core collapses, the rising heat will force the outer layers to swell dramatically. The Sun will expand into a massive red giant, completely engulfing the inner planets and incinerating the very world it once gave life to. After shedding its outer layers into a glowing cloud of gas, all that will remain is the exposed core. Stripped of nuclear fusion, the Sun will end its life as a white dwarf, a dead, incredibly dense ember roughly the size of the Earth, glowing with a fading residual heat. Our sovereign star is destined to become a silent tombstone. Yet, for this briefest moment in cosmic time, its roaring nuclear fire provides the exact, fleeting light required for our blue planet to exist in a cold and indifferent universe.